Starting soon. I can see familiar faces coming in. Harris Camp, Martin Eshiwani. Everybody, please say a quick hello as we wait to begin. We are just about to begin in a minute, and I will invite Professor Winnie Mitula, who is our moderator for the day, to take us through. Prof, over to you. We are 3 minutes past the hour, and we have about 30 participants joining.
Thank you very much, Basil. I know people are still scrolling in, but I really want to say karibuni from Nairobi. It is welcome to this seminar. This is part of the IDS series. Basil, I don't know whether we have the director in here already or somebody standing in for him. Do we have Professor Kamau? Could he be in the audience?
He is not able to join at the moment. If he joins, I'll alert you.
Okay, no problem. So just briefly, this is, we normally at the Institute for Development Studies, which is one of the units of University of Nairobi, largely researching in issues of development and very, very central in the kind of discussions we are having now. We do have weekly seminars. And this particular seminar is being done jointly, the Institute for Development Studies of the University of Nairobi and ULI Africa. And you will be asking, what is ULI? Basically, this is, ULI means ulinganifu in Kiswahili, not far from Symmetry. And it is a loose network of scholars with interest in Africa and more so supporting, graduates, doctoral students, as they go through their research so that they can at least do the kind of research that informs Africa's development. We know a lot of debates around Africa and how progress is limited and how sometimes we are not able to use the right lenses. Therefore, the team of ULI Lose Network is a multidisciplinary team that brings in engineers and even social sciences. And today, don't be worried, we might be having too many engineers, but that's a good thing because in recent times, IDS has done a lot of transport research. And if you know, years back, transport was really about engineering. But right now we know, just as the concept says, the complexity, that transport is not about engineering. So many pieces come into play to inform transport. So if we sit pretty thinking that you only need a transport engineer to sort the African problem of transport, you don't go far. So that's where we are coming from. And actually, we do acknowledge the complexity. And that's why we thought that in this first relationship, I know ULI will be launching itself going forward, but in this first engagement of a collaboration between IDS and ULI, we thought the best thing is to also look at the issue of complexity and how it works out in our system. And there was no better person to do it than one of our own, who is also based at the University of Nairobi, that is looking at traffic signals. And we know what traffic signals are in our cities. Some of us sit thinking that they are the ones that make us get late to work. But I think it's more complex than that. So if we have one student who is trying to conceptualize that and see how he can contribute towards addressing that challenge or putting a system that is much, much better than others, then it's a welcome. That's how we picked Omina. We have so many other postgraduates who will come on board, including Basil, who is actually the one who is coordinating us in this forum, is one of us, again, who has also worked a lot in transport. So one point she will also be able to share with us. So basically, I don't want to get so much deep into complexity, but I think we are going to get into this complexity when we finish, because by that we shall have heard briefly from Amonya, Fred, and we shall also have heard from the student. That these two should roll us out in a way that Elisha Omulo will be able to then respond to the discussion, and then we'll open up the discussion. So I will be expecting the presenters. I think Fred will have something like 15, 20 minutes, and then Mina will also have something like 20 minutes, and then we will have about 7 to 10 minutes with the Prof. Omulo reflecting, Opio reflecting to us a bit on his insights into this topic, as it were. So that's what we expect to have as we roll out. And I think the best approach is for me to first just say, who are these three that has offered to be with us this afternoon? Who are they? So once I give a brief on each one of them, I'll do it together so that when we start running this, it's not like intermittently I talk about them when they are talking. So once I finish, the process will begin by Fred articulating a bit of the issues, and then we'll have a presentation from the postgraduate student, who is James, and then we get to Professor Elisha, who will then provide an overview before we go into discussions. So let me start with Fred, and before I read the written, I must say that I've known Fred for maybe not so long, but I really admire his works and his thinking, which makes me think deeper all the time. And sometimes I call him Professor of Complexity. So he'll bear with me. So Fred is a chartered engineer and fellow, Chartered Institute of Highways and Transportation, holding a PhD in policy science. For over 2 decades, he has peered into infrastructure and public policy across the world, with a special interest in transport. He led the governance theme of a UK development program called Global Transport Knowledge Partnership that sought to bridge the chasm between policymaking and universities of Africa and Southeast Asia. Before COVID struck, for about 4 years, he worked globally as chair transport systems economics at the Permanent International Association of Road Congresses, PIAS. He led policymakers and academicians in attempting to understand transport investment in 122 countries by constructing their policy spaces as dynamical systems. Currently, he focuses on policy structures of Africa, assisting African countries imagine post-COVID world, including steering dialogue on public-private partnerships as a member of the United Nations Economic Commission for Europe, UNESE, team of public-private partnership experts. Last but not least, is actively engaged with World Conference on Transport Research Society. So that is Fred that you will be hearing from. Then we have our postgraduate student and colleague, because he's also teaching at Multimedia University, James Omina, who is a lecturer of computer science and multimedia at Multimedia University of Kenya, Faculty of Computing and Information Technology. Currently is pursuing a PhD in computer science at University of Nairobi in the Department of Computing and Informatics. His PhD research focuses on intelligent traffic light control model based on multi-agent deep reinforcement learning algorithm. He is the author of a research paper titled Intelligent Traffic Light Control System Using Fuzzy Logic Algorithm, published in the International Academic Journal of Information System and Technology. Omina is an active member of networks of scholars researching transport. This has resulted in him being a visiting scholar at UC Berkeley in California, USA, and participating in local, regional, and global forums, including the VREV ITDP-funded Mobilize Santiago Summit in Chile, Mobilize Bogota Summit in Colombia. He is also a member of Kenya Transport Researchers Network that is housed at the Institute for Development Studies, and an innovation fellow at the University of Nairobi Computing for Development Lab, Innovation Hub at UON. So that is Omina that will be presenting to us today. Actually, he is our key presenter. And the topic he will be focusing on is part of his PhD, which is good. Then we have the discussant, Professor Elisha Opio Omulo. Elisha is an associate professor of intelligent systems at the Department of Computing and Informatics at the University of Nairobi. He holds a PhD degree in computer science of the University of Nairobi and a Master's of Philosophy in Computer Science of the University of Wales. He is an expert in a wide range of computing areas, including modeling and simulations and other artificial intelligence areas such as multi-agent systems, machine vision, and embedded intelligence systems. Professor Pio is active in research and has been a co-director and a health informatics tackle lead for HIV/AIDS project for over 7 years. His research areas of interest include applications of artificial intelligence in various sectors, including education, health, and technology. He's widely published and was a member of the British Computer Society Expert Systems Specialist Group in 1996 and 1997. So colleagues who have joined us so far, I can see you are about 57. Those are the people, the 3 scholars who are going to share with us insights into this topic of today's discussion. So I will stop there and straight away call upon Fred Amonya to have a shot at the discussion. Fred.
Hello. Hope you can hear me. If you have any problems, Winnie, please, just raise your hand.
Okay.
And thank you very much for that introduction. Now, I would be very glad to see your faces. If you can, please turn on your video.
Fred wants to see that he's talking to human beings and not robots. Okay?
Yeah,
so those who can
that is right.
Let them turn them shortly, and then they will switch them off for purposes of those who may be having lower bandwidth.
Exactly. Okay. Right. I can see quite a few friends in the room. I will not pick you up individually. We've met at different places, but I must say, what a pleasure to see you again. Now, today, the main play is our doctoral student. The main play is our doctoral student, and our work is to create a deep swimming pool for him. I want us to create a deep swimming pool so that when he comes in, he can dive so deep without banging his head. That is the challenge we have. All right? So we will go straight away to our main slide. Basil, I hope we can do so while keeping quite a few faces on our screen. We'll do the next. This one doesn't really matter much. It's African complexity, the enigma of symmetry. Okay, friends. What is all this stuff? That's my question. That is our question. I hope you can see all this stuff on the screen. What is it anyway? I think that question is my keynote address today. And maybe I don't have to say anything. Winnie, I might not have to say anything. Maybe I've done it. I don't have to talk like Fidel Castro. That is not necessary. Okay. Now, if we look at that screen, right from the top, diagonally all the way to the bottom right, the Rubik's Cube, and then a little equation at the top right, and another equation top, bottom left, and beautiful pictures in between. The question is, what is all this stuff? I know we have quite a few graduate students in the room, and I want to challenge us. Is there any of us who would not, in one or another, identify with at least one item of collage that we have before us? I hope the answer is no. We have the shuka there, the beautiful shuka there. We've got a cactus there. We've got an equation that I want to think that we loved when we're doing our secondary school education, all of us. when we're doing mathematics at O level, the quadratic formula. Then we have a few faces, and we've got a couple of equations. What is interesting is that all this stuff we have before us is one. These are just different faces of symmetry. Hello? These are just different faces of symmetry. But how can symmetry be so weird, so elusive? It's common, it's everywhere, and yet it can escape and be nowhere. Why is symmetry an enigma? Why? And if we dig through a few of them, you'll notice one of them is in red. I wish I could ask. I wish I could ask us to guess why. Why do we have one of them in red? Why? The one in red came up about in the 1530s. Let's say the 1500s. And it's at that time that the sociology of mathematics was settled. I just said sociology. Don't think you misheard me. I just said it was at the time that the sociology of mathematics was settled. And in the 1500s, we could have created the modern world as we know today. Now, someone must be asking, hold on, what do you mean? What do you mean that the sociology of mathematics was settled around 1500? It was at that time that the square root of -1 was admitted to the human fabric. And the square root of -1, which picked on the misnomer, imaginary number, has guided the world to where it is. I'm tempted to run quickly through at least the faces. There is the young man in the middle. The name is Evariste Galois, the 1820s. He opened up the symmetry we know, the symmetry you experience every morning while looking at the mirror. He opened it up as a mathematical object. Then the lady next, that was around 1890, was the brain of Einstein. I just said that lady was the brain of Einstein. Her name, I hope the chorus comes up, Amy Noether. She made sense of the symmetry that allowed Einstein to illuminate our world, bringing us most of the modernity we enjoy today. Right at the bottom, there is a young man. Many of you will, a few of you probably will have been to Westminster. What is interesting is that that young man features is inscribed right on the heart of Britain. And yet the name never features when Britain is going out. I keep wondering why. His name, Paul Dirac. And his argument was simple. If it is true, it has to be beautiful. If it is beautiful, there must be symmetry. The one next to Paul Dirac, those three equations, that is where the world is parked today. The SU3, SU2, U1, that is where the world is parked today. That is about all that you and I know today. That is about all that humanity knows today, the so-called standard model of particle physics. The world at a very all of us in this room, if we're to wake up, if we're to go down, we look at the tiniest of us all, we would belong in that world. So that's about symmetry, the enigma, friends. It's running everywhere. Now we must have a few questions to ask, and we'll go to them. Can we go to the questions that follow? All right, so friends, why is symmetry? Why is symmetry beautiful? Just why? I'm not going to ask us to answer that question today, but let's carry it with us. Why? What should make it so beautiful? Why is it ubiquitous? Why is it elusive? And fundamentally, why is symmetry so effective at predicting our world? Now, where is symmetry in the messiness of our public space? If we are going to make sense of public space, and we are going to look at a picture of that, and our doctoral student is going to open up the mess of traffic. If we are going to make sense of the mess of traffic, then we have to engage with symmetry. We have to engage with deeper symmetries than we know today. The graduate student will also talk about AI and how we can employ AI. But what's AI and where's AI in our story? Artificial intelligence is nothing but linear algebra. Artificial intelligence is the machinery of linearization. A time when we decide to break up whatever is before us and do it in a way that is additive. The problem is the real world is not linear. The real world is not linear. And that is the challenge we have. And the final question, what brings us here? This thing called education. Remember I said, we've got to construct this deep pool so that our doctoral student can dive in freely. He knows that the pool is there, he can go wherever he wants. So the ultimate question is, what is the place of education? What does it mean? I would like you that I keep telling the doctoral students in this Muzungu land that keep telling them that there's doctoral study and there's money. If you want money, you might not have to do a PhD. We're going to listen to a PhD. So if you want money, you may not listen to a PhD. I think the challenge we have today, my fellow Africans in the room, now I'm addressing you directly. We are conflating education and money, and that is causing all sorts of trouble. The two are not independent, but they are the same, they are different. So we must challenge ourselves to ask regularly, what is the place of education? And I keep saying, if you're educated, you can't steal. I just said that. If you're educated, you can't be stealing public money. So education has got this unique place that is above industry, that is above money. Can we find that place of education? The other day, one of our leading, a vice chancellor from one of our leading universities was complaining about how the training of their students is not geared to industry. Wait a moment. The university is not there to train for industry. The university is there to guide industry. Have we come so low that our universities now train for industry? Have we come so low that our universities now follow industry? See, these are the challenges we have beyond the specific discussions we are going to have today. Okay. Now, the next slide is going to set the stage, to open the stage for our doctoral student. Could we go to it? Right. We are familiar with that one. That is what we are going to tackle today. If we are going to sort out that mess, we must hunt symmetry. And hunting symmetry is going to require that we mathematize that space. It's easy to see that we can abstract from the messiness before us and find the state, find society, and find the market. In our Africa, the state is young and molding, going back to the 1960s typically. The market is just mushrooming. Society is old, but was severely battered in the post-independence turmoil. At independence, society and education, for example, were well linked. So society had a bridge of trust, a plank of trust with the elite of that time, with the graduates of that time. That has gone. So we've got to pick that mess, we've got to abstract from it, we've got to see the state interacting with the market and with society. And as we work through that interaction, which we call it the dynamic ecosystem of the mess, that mess before us, we will need to use symmetry. I said, it's not my work here to talk like Fidel Castro. The main play is a doctoral student. And I think it is right to hand over to the doctoral student.
Thank you.
Thank you, Winnie. Thank you all.
Thank you very much, Fred. The hunter is being called on the stage, and the hunter, I think, is very ready. So the hunter just bang on. Get us the animal that we are looking for in the name of traffic.
Thank you very much, Prof. I can't take it for granted that you have allowed me airtime to address the issue of congestion in our cities, and I want to seize this opportunity straight away. Let me share with you my slide. And okay, so let me see. I want to share the slide. I hope you are able to see the slides.
Yeah, I'm able to see it. You can blow it up if possible.
Yeah, I'm seeing. Let me. Okay. Is it okay now?
Yes, sure. Go ahead. Go ahead. You are good.
Yeah, today we are going to look at how to control traffic. We are not saying that we don't have intelligent traffic light systems. If you go to these advanced countries already, they have implemented quite a number of intelligent traffic control systems. But that does not mean that research on intelligent traffic light system is going to stop, because we continuously are yearning for better systems. And that is the basis of this research. So I'm going to use an algorithm which we feel will be far much better than what is there now. So I'm going to use two types of AI concepts: deep learning and reinforcement learning. And when we combine the two, we call them deep reinforcement learning model for intelligent traffic light systems. So the other intelligent systems might be having, either they can have human intervention, which is the best intelligent system, but with a lot of shortcomings. And they could also be having other algorithms like fuzzy logic, like the one I told you I published. But you will find the limitations in those other algorithms, which the new algorithm is, the deep reinforcement learning algorithm will address. So on the background, you can see a traffic light, and the traffic lights and
it's not moving. Can you try to move the slide? It's still on first page. And that background, you can go next if you have to move it, if you had moved beyond that.
Yeah, so we are saying that Africa is actually the home of civilization. Civilization started in Egypt in the year 1600 BC, and we had animals, and probably later on we came to wheeled vehicle transportation, which was widely used in Africa. Then recently, Africa has experienced a lot of growth in terms of vehicles on our roads. There are increasing number of vehicles that are actually coming into our roads. And therefore, it has brought the need for improved traffic management. And most cities in Africa, Nairobi included, have no signalized intersections. When you make your observation around, you realize that most of our intersections, or what we call roundabouts, have no signalized intersection outside the CBD. And this has contributed to traffic jams and delays. And therefore, over the last few years, intelligent transportation systems have been introduced to create symmetry or balance in approaches to address complex issues among infrastructure and human behavior at intersections. So the use of intelligent transportation systems can improve, of course, with a focus on intelligent traffic control system, can improve the efficiency of transportation and traffic flow. And when we improve traffic flow, we reduce emissions and expand capacity of our infrastructure. When I talk of expanding capacity, you've seen, we've witnessed the expansion of Thika Road, and that has not solved our problem, because the more we expand the roads, the more traffic builds in, and the more traffic jams occur and delays and so on. And I know most of us, right now, we are even avoiding Thika Road. I have friends who live along Thika Roads. They prefer to use the Eastern Bypass and then go to the expressway and to come to town. So you can see that expanding the roads or infrastructure is not actually the solution. And what are these factors that I'm talking about? We have increased number of vehicles. We have things to do with poor urban planning, increased urban population. All these are factors that are bringing in growing need.
Are we losing you, or is it me? Basil? Basil?
I think it's James. We are
it's
losing James.
We're losing him briefly.
James, we have lost you.
You have lost me.
Oh, now you are back. Yeah, now you are back. We lost you a bit.
Okay, so let me go back.
Yeah, you were just finishing that PowerPoint where you were giving context. And now
Yes.
you are at effects.
Yeah, I was
effects and solutions. Yeah.
Yes, and I came up with solutions, so like what we have in Kenya, quick construction of roads and so on. But as I was telling you, in constructing more roads is only bringing more traffic, and it is not helping us with the capacity. But what about, the government has been toiling with the idea of introducing intelligent traffic systems in Nairobi, but so far the implementation is partial. You find that areas like Upper Hill and maybe other posh areas have already implemented a bit of intelligent, but Nairobi CBD is still not configured with intelligent system. So what are the problems? The problem at heart is the problem of congestion. Of course, when I talk of congestion here, I'm talking about traffic jams. And what is actually contributing to this congestion? We have signal configurations. Signal configuration are what is actually triggering the change from green to red and probably yellow. Actually, that configuration is not efficient, and especially in the CBD, because it is time-based and fixed. We also have an occurrence in our cities, especially in the third world, where we have uncertain state of queues and arrivals, maybe due to incidences, which we don't manage very well. And also adjustment in intersection of, in a particular intersection. You might find that the adjustment of traffic light at a particular intersection can affect others that are neighboring. And then there is also the spread of congestion to many other intersections. You find that when there is a traffic, when you try to clear traffic on one isolated intersection, it can easily spread to the intersection on the nearby. So in effective time management, well, most of the time we don't know how much time to allocate for a particular route so that we can be able to reduce the traffic congestion on a particular route or link. Then most of our traffic lights are not adaptable. They don't change according to the density of traffic in that particular intersection. And also we don't have a system for prioritizing emergency vehicles. And therefore we are saying that ensuring traffic control at intersection is still a challenge, and reducing congestion should be a priority. And traffic signal at intersections in crucial areas need development, continuous development. And therefore the introduction of intelligent traffic management is needed to replace the conventional traffic lights commonly found in African cities. So the existing fixed time control system which we employ is not efficient, and that has been proved through the literature and through the studies that have been made before. So the objective of our study was first to identify the factors that contribute to traffic congestion and which I have highlighted in the earlier slides. Then two, we want to design and develop an intelligent traffic light control model using a machine learning algorithm, specifically the deep reinforcement learning. And we shall evaluate the performance of the model in comparison to traditional traffic signal control method commonly used in and around junctions in Nairobi. And lastly, draw conclusions and recommendations for possible future considerations. And the research questions are quite, of course, I don't need to ask them. We shall see at the end how the research questions are mapped to our objectives. So we did a lot of studies, and I focused more on the different algorithms that have been used in the literature. And we found quite a number of deep learning algorithms. We want systems that are learning, not only intelligent, but can learn just like a human being, can store information and use it for further improvements. So we have authors like Abdus et al., Abdullahi et al. 2003. They studied a lot of Q-learning algorithms in combination with ADP. And the authors applied Q-learning method in non-stationary environment. And the difficulty in finding proper parameters for given traffic demand, it was found that Q-learning are poorly suited to multi-agent environments. And current research and others incorporate other parameters. That is how the gap which they found was addressed. Apparently, I'm not able to read beyond that. There is something which is, okay, there was some gap which they realized, and they proposed that in future, their study will focus more on multi-agent traffic control systems. Another group of authors called Alt, Ann, and Sharon in 2020, and Kos et al., among others, they also did a lot of research on deep Q network. You see, Q-learning is just the normal reinforcement learning, but now deep Q network is a deep reinforcement learning algorithm. So they made an improvement on Q-learning, but the authors found that even with this deep Q learning, they found that deep Q network cannot cope with complex traffic scenarios like the ones in Africa and cannot easily be interpreted and regulated. Other authors like L.I. et al., Casas, and so many others now introduce the concept of deep deterministic policy gradient and other multi-agent deep deterministic policy gradients. And they found that deep deterministic policy gradient, abbreviated as DDPG, is not able to properly control the traffic in real world. And the DDPG require more hyperparameter training or tuning, and therefore takes longer training times. So they found that for them to make their algorithms better, they need an enhancement and incorporate coordination mechanism in their algorithm. So after the literature, I came up with the conceptual model framework where I had my variables, the input variables, and the control the process of processing my variables to give me some measures of performance like delay time, travel time, throughput, and so on. And every time I get that, I get a constant feedback, which will allow me to make my control system work better. So there were data which we collected, traffic volume data, and traffic volume as well as time-dependent origin destination matrices were gathered from 2 video cameras placed at strategic points in a selected roundabouts. Time gap distribution data was also collected, and this data was mainly collected in the morning, especially from 6 to around 8 in the morning, and in the midday from 12 to 1, and also in the evening from 4 to 6. And those are the times when we normally have high traffic in Nairobi, or what we call peak times. And there were also turning movement counts. Traffic data was manually collected at all the 5 roundabouts, which were the target roundabouts. And the turning movement counts were also done between 10:00 hours during the AM peak period and 18:00 hours during the peak in the evening. So the top diagram shows the conceptual model framework, and the diagram just below is going to show our system structure, which is actually the overview of how our traffic light control system works. So from the figure, you can see that the system contains 3 parts, namely vehicle started information acquisition part, and then we have the joint execution of signal lights. Once we have got the data from maybe cameras and sensors, we can store them temporarily and feed into our control system. And then from the control system, depending on the algorithm that we have configured, the trigger from green to yellow to red can take place with comfort. So we are saying that we came up with, this is how we can visualize the model, which is being controlled by deep deterministic policy gradient. And this time we are introducing an attention layer into our model so that we focus only on those parameters that are relevant, but we ignore those that can only make complexities, because our model should be as simple as possible. So the top diagram is the deep reinforcement learning with attention layer, and priority sampling was used that made improvement from the unified layers, and it represents the control algorithms using reinforcement learning. So you can see some of the parameters. We can collect speed, distance between vehicles, and the speed of movement of those vehicles. So through these speed parameters and distance, we know that when there is traffic jam, the distance, the vehicles are very close to each other. So the distance between the 2 vehicles will be close, and also the speeds will be very small, I mean, very minimal. And like when there is no traffic jam, the vehicles tend to move with a lot of speed, or they take, the action that they take is accelerate. So experimental settings, we have simulation process. We used a simulation to run our model. And you can see we were using SUMO, which is a simulation of urban mobility. And from that, we were able to generate a number of results. Of course, the algorithm which was running the model is the fault tolerance attention multi-agent deep deterministic policy gradient. And then the results of the study were as follows. So you can see that after implementing the model and the algorithms, we were able to compare the performance of the fixed time algorithm, the multi-agent deep deterministic policy gradient algorithm, and then the attention multi-agent deep deterministic policy gradient. And the number of vehicles that we took into consideration were 5,204. And all junctions, the vehicles that were able to pass at a particular time were 960. And this GNO, these are like intersection 1, intersection 2, like that. So intersection 0 was, I took El Salesia. Intersection 2 was the one at just near railway. And then there was another interchange at the former Barclays Bank, Moi Avenue, and the University of Nairobi roundabout, and the GPO roundabout. And we were able to calculate the average waiting times for all the junctions with a fixed control algorithm, and also with the different multi-agent deep deterministic policy gradient algorithms. And each of the junction had a four-way intersection. And the graph you can see on my left illustrates the attention multi-agent deep converges after about 2060 training episodes. And this confirmed faster convergence of the algorithm as compared to the others. We also got the average travel time for all the algorithms, and we were able to find that averagely, the travel time is lower when you use the attention multi-agent deep deterministic policy gradient. And we also took the average queue length as another measure of performance, and we found that the attention multi-agent deep deterministic policy gradient had at the lowest average queue length compared to the others. And therefore, we made performance variation with traffic demands, that is depending on the volume of traffic that are approaching a particular junction. So the graphs here illustrates that average travel time increases with increase in traffic density. And the result further illustrates that multi-agent deep had best performance and studied that, meaning that the attention multi-agent deep deterministic policy gradient lower average travel time by 16.21 at high traffic demand. And this indicates that attention multi-agent deep deterministic policy gradient had an excellent prospect in dealing with intersection control and is better than all the other baseline algorithms. So the average queue length at high demand was also measured, and the attention multi-agent deep deterministic is shown to have the lowest average queue length. And fixed time algorithm had the highest queue length, and that increases sharply with the increase in traffic demand. So the implication of research finding, the outcome of the current research is an active influence to the address of problem of traffic congestion. The proposed algorithm in the current research will solve traffic congestion problem at traffic circles that result in jamming in all directions, causing queue spillbacks at congested networks. And the model addresses the challenge by allowing signal-controlled crosses or intersection, in which case only the approach upstream is blocked, while the other traffic towards the crossing direction flows without impediment. So the proposed algorithm would reduce waiting and travel time compared to the other two baseline algorithms. And the proposed algorithm would improve vehicle throughput and average waiting time at intersections. In conclusion, it was found that the monitoring and controlling traffic in Nairobi is sufficient to maintain traffic flow in the city. However, the attention multi-agent deep deterministic policy gradient has been found to perform better than the other deep deterministic policy gradients and other fixed time algorithms, thus reducing traffic congestion, waiting time, queue length, and travel time. Therefore, attention multi-agent deep deterministic policy gradient will solve congestion problem of traffic circles that result in jamming in all directions caused by queue spillbacks. And the algorithm addresses the challenge of all-round jamming, allowing signal-controlled crossing, in which case only the upstream is blocked and allow the flow to flow impedimently without any impediment. So the implementation of the attention multi-agent deep deterministic will improve throughput and lower average waiting time. And therefore, attention multi-agent deep will improve passenger throughput as well, because when we introduce dedicated lanes, as now that the government is considering BRTs and other dedicated lanes like expressway, we find that we shall be having a better flow of traffic. So the recommendation is for future research, we can develop this model by focusing on the area of synchronized signal control at traffic cycles to create a green wave. And in future, we also want to improve this algorithm to enhance cooperative traffic network, which is traffic network at a given length. Like if you open the vehicles at Haile Selassie, the vehicles should not go and get stuck at GPO. They should find the traffic signal also opening so that you create a continuous movement. And to further verify the effectiveness of the algorithm in real dynamic control, it should be tested under more complex and various traffic conditions in the African cities. Thank you.
Thank you. Thank you very much, Omina, for sharing with us your work on intelligent traffic light control model and with your proposed model, which I'm sure a lot of people will be waiting to engage with you in terms of how it works, issues of control and signal, and how it's going to be very different from the others. But before I go there, and as I wait for people to keep chatting, post your comments and everything, because the team behind the scenes is going to collect all those concerns and comments for later discussion when we, after we finish listening to the respondent, Elisha, who just wants to give some reflections in both how Fred framed the issues and how James has responded by at least sharing with us one output of a PhD that is trying to address one of the complex challenges that African cities face. So thank you very much. I now invite Professor Elisha Opio to just weigh in as well. Thank you.
Thank you very much, Professor Mutula. And also, I want to recognize our colleagues. I want to thank our earlier presenter, Dr. Monya. And also, I want to recognize all participants. This is a request from the moderator. Mine is to really engage with the presenter so that members can benefit. And also we connect the theme. The theme is very, very interesting. And because I want to engage with the presenter, the moderator will allow me. I think that way, the participants will get more insight into what's going on, and also connected to the theme. And interesting, the people, scientists are generally in the lab, but this is a situation where they have been pulled out of the lab and exposed to philosophy. And it's very, very interesting also how they are going to behave and to interact. And with that, let me start straight away to engage the presenter. So the first thing we think about is the symmetry in traffic systems and African urban complexity. And so we want the presenter to briefly highlight how deep reinforcement learning model addresses enigma of symmetry in traffic systems, especially in the context of African cities where the flow of traffic is often irregular and predictable. And the issue is, could there be hidden patterns of symmetry within this complexity? So, Adunya, you want to say something on that?
Okay, thank you, Prof. I would like to respond to your concern on how deep reinforcement learning would address the enigma of symmetry in traffic system by dynamically adapting to complex and irregular patterns. So in the African cities, where traffic flow can be irregular and also asymmetric, deep reinforcement learning model can learn to manage these conditions effectively through adaptive learning, because it is a learning model, dynamic decision making, because once it has learned, it is based on the previous experiences, it can learn new ways of dealing with the situations, and also the scalability. You see, deep reinforcement learning is scalable because of the multi-agent case, and it can also accept real-time traffic information to help it make decisions.
Thank you very much. Thank you very much, presenter. How about the unique African traffic challenges? African cities are characterized by a mix of formal and informal transportation systems, along with rapidly changing infrastructure. Will your model adapt or learn from these complexities and symmetries in traffic patterns?
Yes, within the complexity and apparently irregularity of traffic systems in African cities, there is usually hidden patterns of symmetry. Deep reinforcement learning models might uncover and utilize these patterns by classifying the emergent behavior, spatial and temporal patterns, and clustered behaviors to make them recognizable and therefore make better decisions.
Thank you very much.
I don't know whether I've satisfied you, but
yes. That's all right.
okay.
Now, just the role of symmetry in optimizing traffic flow. You know,
Yes.
symmetry, sometimes you can see it from the balance point of view. The presenter also referred to this as beauty point of view as well, and also the order within the system. So in your research, do you aim to create symmetrical traffic patterns through reinforcement learning, or does your model embrace and optimize natural symmetry found in African traffic flows?
Well, thank you very much. Maybe I will answer by addressing what we mean by deep reinforcement. I mean, with the reinforcement learning is a model free in that it does not have existing data to pick, but it can learn from what is there in the environment. So the deep reinforcement learning model can be designed to address these social implications by considering inclusive data collection, considering comprehensive data sources, and gathering data from a variety of sources to capture the full spectrum of transport modes and use experiences, including those from informal transport systems. And this will ensure that the model understands and considers the need of all user groups.
Okay. Thank you very much. I'm also interested in how you'll react to the handling of symmetry in data and traffic dynamics. You see, data and traffic patterns in African cities can often be incomplete, inconsistent. So how does your model handle this data asymmetry? And how do you ensure that it remains effective in the face of such challenges?
I think what you are simply asking is how scalable is my DR model, or am I wrong?
Yes, you're right.
And how does, the deep reinforcement model can handle these challenges by implementing modular and scalable architectures, such that we develop the model with modular architectures that can be easily expanded or updated as new intersections come by the way. So the emerging traffic patterns can be allowed, the system can allow the emerging traffic patterns to integrate new elements without requiring a complete overhaul.
Okay, thank you. Thank you very much for that. I'm now keen to hear your view about the symmetry reward structures for the reinforcement learning. A little bit technical this time. So you see, deep reinforcement learning, there will be as a reward structure, and that is the key in it. So how do you design your reward structures to encourage symmetry or balance in traffic light control, while accounting for the complexity in real-world traffic conditions in African cities?
Okay. When we talk of scalability, we are trying to address complexities with our systems. And therefore, we shall try to collect data that will translate into better decision-making for our algorithm. And that way, we shall improve the efficiency of the traffic control system. I may.
Okay, thank you very much for that response. And now I think for the sake of the audience and for the sake of time, I want to jump to a few last questions, if you don't mind. So I want you to say something about the implications for policy and practice. I also want you to say something on ethical considerations But in terms of policy and practice, it's interesting what the potential policy implications for this research would be all about. So how can governments and transportation authorities leverage these findings to improve traffic management?
Okay, I would explain it this way, that the findings of this research can be leveraged to create more and effective and sustainable traffic management policies. And these policies will be data-driven, decision-making by the government. The governments can use insight from the deep reinforcement learning research to develop data-driven traffic management policies. And by leveraging real-time data and advanced analytics, policies can be based on empirical evidence rather than intuition or outdated models.
Thank you very much so far. Mainly my final question, and this is about the ethics and ethical considerations. So in your view, are there any ethical concerns associated with the use of AI in traffic management? Mainly you may think about privacy issues or potential unintended consequences.
Well, where the use of any model is concerned, there is ethical concern as well. And this can include these privacy issues and the potential for uninterrupted consequences can bring our model not to work properly. And here, I did a look at these concerns of privacy issues in traffic management often rely on extensive data collection through sensors and cameras and GPSs and so on. And this can lead to concerns about surveillance and potential for invasive monitoring of individual movement. Again, data security. The data that we have collected must be secured and stored in a protected from unauthorized access by others who can use it to misuse or expose personal information. So the issue of ethics and ethical concern is there. I can't deny that.
I want to take this opportunity to thank the presenter a lot, and also because the moderator also suggested I summarize, I also want to thank the researchers involved in this research, because in their results, they have benchmarked their outcoming with 3 algorithms, and they have consistently demonstrated that their algorithm is performing better all the time. Interesting, because it is traffic, beta is short. You see, if it was money, beta would be large, but here the beta is short. So their algorithm is actually consistently demonstrating that it's actually reducing the traffic congestion. And this is very, very interesting. I think the presenters also reacted to the philosophical connections of his work and also highlighted the African dimension. Incidentally, the Tom Boyer diagram that we were given, remember, it really looks chaotic, but we know in Tom Boyer there's a line in between for the traffic on the left and traffic on the right, and that if the members are encouraged to drive along like that, they would flow well. I must thank the promoter of this, and also the director of this discussion, and the opportunity that we have had to present. So I think I take it back to Professor Winnie, who can now open it to the larger community. So thank you, Prof.
Thank you. Thank you very much. This is what we expect for those who may not. This is the unique aspect of WULI, in collaboration with IDS, because the whole idea is that we engage the student, we support the student so that the student can advance his work and also interact with some of the positions that others might have. For example, I've been through this work of James Omina for very long, I think from proposal stage. And I know at no point was the issue of symmetry a discussion on table, but we can then get back to Fred and acknowledge that Fred's position that symmetry dictates a lot of things is quite implied, because Omina is able to talk to symmetry, having not conceptualized his work as a symmetry issue. So I want Fred to at least say something. I know we have a lot on the panel, and Basil and your team, be ready. I can see there is, I think, something that came from Harry's Kalakam. Harry, I'm going to ask you to articulate it so that Omina can interact with it, because it's very crucial. After Fred makes a few observations, then we will get back to the panel after Harry, and then we can get to the plenary. Fred,
my friends,
having listened to this discussion and presentation, and having reflected in what you presented as a conceptualization, what would be your response to the work of the postgraduate student that is going to address one of the challenges that is facing us in our cities?
My friends, I'll be very brief. I want us to go back to the audience to take their questions. That is way more important. But I'm going to tell us a quick story. In 2004, UEFA European Football Championship was held in Portugal. And if you remember clearly, in the 90s, this country, Britain, was notorious for violence. Football stadium, the country was banned. You remember that. But in 2004, what surprised people is that in Portugal, the only cars that were properly parked, remember they were so scared of British funds. The only cars that were properly parked were British cars, British number plates. People asked, how can these drunkos be so organized? I mean, and that speaks a lot to the challenge we have. When I look outside here and I think of the roads around me, the volume of many of them compare well with our most trafficked roads. They use roundabouts, and those roundabouts work very well, seamlessly. And the big word is respect. Respect for the commons. So I urge us this afternoon to look at the challenge of traffic, not as one of technology and even engineering. No, it is a sociological challenge. It's fundamentally a sociological challenge, and we must tackle it at the point of sociology. And of course, sociology resides in history, but ultimately, whatever happens before us, to make deeper sense of it, we need mathematics. That's why I concluded by saying, in this, we have the state, market, and society engaging. How do we understand it? How do we abstract, understand it, and come back with a position that our people can access? That is the biggest challenge we have. And going forward, I run across graduate schools, University Hills of Africa. The one thing we don't do well is take on the challenge of complexity. Most of our work is still resides on the old Newtonian frame. That is the so-called F equals ma. It's a linear world. The world is not linear. It's difficult for us to muzzle all the forces onto one and look at it as a challenge of regression. So we've got a task before us. I'm indebted to my colleagues, Winnie. Martin was online somewhere, maybe at one point. Winnie will bring her on board, and perhaps a few others. Okay. I'm indebted to them for saying, oh, wait a moment. Can we, under this umbrella called WULI, go out and challenge the way we address our complexities while doing doctoral research. And I think I'm glad you're with us all, Winnie, Martin, and any other who's online. I think I'll leave it at that. It's more important to hear from the audience. Thank you.
Thank you very much, Fred. That's a good observation. Harry, can you just bang on, please, and just get on board? Harry?
Thank you, Winnie. But you're putting me on the spot here.
Yes.
So for those
you are my old colleague who went through this some years back.
Yes, we've had plenty of exchanges. James, I think in academia, we're in the privileged position to both prove what works and what doesn't. And my question, I see links to what Kevin and Peter later on posed. Roads are complex spaces. They're not just about traffic. Things happen there, things land there, rubbish lands there, animals cross. And throughout all of this, people just don't listen to the technologies that we place on the roads. And there's the reality, and I've been to Kenya and specifically Nairobi several times, that people just don't listen to traffic signals. Now, it's not criticism on you, it's the way that people behave. And so roads are social spaces too. But perhaps the bigger comment here is, I see you've adapted the work of authors from outside Africa. And I think part of our responsibility as researchers who work in and on Africa is to both prove and disprove work from outside, whether it's on technology or other spaces. And I think, you have a fantastic opportunity here to prove whether these models work and to adapt them. And so the question I posed in the chat is whether your model can compensate for humans ignoring traffic signals. I mean, there's an enormous contribution you can make here. So I want to encourage you to go deeper and to disprove as much as prove what is possible and what isn't.
Okay, do you need my reaction, Prof? Harry Scarlett?
Winnie, you're on mute. We didn't hear you there. Perhaps you'd like to moderate this.
Oh, sorry. I think we can have, take that down. Let's have two others, then you can address them together. Yeah. Basil and technical team, are you there from the panel? Let's check what is in the chat.
Yes, there are some questions. I would like to
Pick
take
the
the very first one.
Okay.
There is Kevin Dome.
Let's hear Kenneth Obogi. Kenneth Obogi, you can go on. Basil, try to put your act together. Let Kevin, who is online, can just talk as you see which ones you want to float. Yeah. The next one to make 3 and then another 3.
Thank you, Prof. I hope you can hear me. Our roads are a bit noisy here in the university. Can you hear me?
Yes, I can hear you very well, Prof.
All right, thanks, Prof. My name is Kenneth Mbungi. I'm from the Department of History and Archaeology. I mean, a wonderful presentation, particularly to a historian like myself. The closest I've come to science is my interest in history of science, history of water and sanitation, and the history of malaria control. That's the closest I've come. So presenters, please forgive my ignorance. But I wanted to pick from where Dr. Monya left. How do we interface technology and culture? That's my very simple question, because by technology, by the way, I mean by culture, I don't mean the traditional understanding of culture as a category that connotes old, past, obsolete, but I use it to mean what defines people's identity and who people are. That is the context in which I use the word culture here. And I may ask the same question in a slightly different way. If we talk about intelligent light system, can we also talk about intelligent people? and those who are not so intelligent socially. Because if you are here in Nairobi, in my nation's capital, I have a sense that we need some training in social intelligence. If you drive on our roads, people have no respect. I think Dr. Amonya referred to that, mutual respect for each other. Our sense of shame is not very high, particularly when we are on the roads. And finally, there are very clear characteristics of emotional immaturity, which some people euphemistically call road rage. So how do you interface these intrinsic of our day-to-day life with technology? Because I think that is what.
Ken, you are mute. Did you finish? You are mute. Or that was a... We can't hear you, Ken. You are mute. You muted yourself unknowingly. Okay. Now you are
Okay.
off.
I'm done now.
Thank you very much. Thank you very much. Basil, one more for Omina, then he can bang on the three. But the last two are very related. Yeah. Yes, go ahead, Basil.
Yes, maybe I can put two, just the main ones in the chat.
Yeah.
Peter Omondi says that the model proposed by Omina is a versatile response to urban traffic challenges. And he's asking, can it be scaled down to respond to challenges with the safety of wild animals in designated animal crossings, for example, on roads that traverse ranches, reserves, and parks? Number two, Kevin Dome says he was looking at it from social and human behavior perspective. So his questions are, does this research put into consideration Kenya's bad manners, taking turns at non-designated places, and how to curb this? And two, the case of police at the, of course, police officers at the junctions and roundabouts, who mostly cause traffic jams. And building of booths to monitor traffic flow by offenders at junctions at clear roundabouts. Just those. Over to you.
Thank you. Thank you very much, Omina. You can see people are loading in a number of factors that they would want to know whether those attributes or variables were ever loaded into your simulation. So I think you can respond to those ones, and then Basil will look again when there are others, and I'll also be attentive to hands in case hands will just, you can merely raise your hands if you don't want to bother yourself with typing. Okay, go ahead, Omina.
Thank you, Prof. I will start one by one. I will start with Harry's question about mixed traffic in Nairobi. And I would say that my deep reinforcement model can address these informal elements like these minibuses, the notorious minibuses, the matatus. I don't know which one is matatu and which one is minibus, street vendors, and very many other complexities that are associated with the African traffic systems. So my model, or what I'm referring to as deep reinforcement model, can address these informal elements by incorporating data integration from diverse sources, by using GPS data, mobile apps, and traffic cameras to track the complexities, and also to track the order of symmetry, or what we call the model can navigate this balance first by understanding the oscillations and by adopting the learning mechanism within the reinforcement learning model that can continuously learn from real-time data and adjust its strategic dynamically. So with time, we can improve on the model. Although as at now, I focus more on the cars and probably vehicles, but we can make an improvement. That is why it is a continuous learning model, such that there will be need to incorporate this other type of or mode of transport into traffic control, then we can make sure that the traffic is improved by accommodating those other modes of transport. I don't know whether I'm satisfying my questionnaire. The person who asked.
I think you have to tie that with the question from Dr. Obongi of interface of technology and culture. And also you have to take into consideration the fact that Africa is very scarce of data. So when you are saying you are able, the system is able to, that's an assumption, maybe you can just confirm to us, an assumption that with availability of data, if, for example, data of the likelihood, you remember somebody has asked about animals. I don't know how one simulates for those animals, which might be, the wild animals, which might cross, taking into consideration that Nairobi is actually in a national park. So are those things that are doable, or the way, does it allow for that, even if looking forward? And then, of course, you can also reflect on the issue of data and availability of data, because with cars, it's very easy. Engineers can go onto those roads and do vehicle counts, but even human counts are never even done so well. But I think vehicle counts tend to be done and simulated. But when it comes to other factors which might intervene, sometimes there is a challenge, although you are saying that the system can take it up. So you can reflect on that, and also the interface of technology and culture. Our culture, our practices, where we even don't care about that traffic signal. It is red and I'm going. I think those are the kind of culture that is being referred to. The institution, the norms that we have embedded, some of them are not very viable with technology because they don't run on technology intelligent system, but it's just, you don't know, you can't predict what one, pedestrian will do or what one motorist will do. And some of these motorists have even crushed people when actually they shouldn't go. When at red, they were trying to go. So they end up in conflicts of vehicle to vehicle. So just a bit of observation, if you have any on those issues.
Okay, for culture, I think we should just create an awareness every time we implement a new technology. Somebody had suggested during the presentation that we should create room for maybe forums where we create an awareness on the citizens to know that there is a new technology that works like this. I think that is a work the government should take, an initiative that the government should take, because without the citizens being made aware, they will keep on vandalizing and probably disobeying and not taking great care. And that does not just happen with the traffic control system. It works with other infrastructural systems that we have in Kenya. So that is just an awareness that can be done by the government or by stakeholders who feel that people should be made aware that the importance of new technology. So the issue of culture is a bit hard, and those are the reason why even in my model, my model is full of assumption. You see, you cannot create a perfect model because a model is basically a simplified system. If you go if you take all the complexity, then the model may not work. It may not give you the result. So the model must be very specific. Like now, in this case, my model was, can we have more efficient algorithms to help us control traffic, to help us control vehicles on our road? But when you factor other complexities like cars, like animals, and I think the model would be too complex and it may not be easy to work on it.
And that's the complexity of Africa. Now, probably you need to tell us something about the signal control. I'm just trying to use my experience in African cities where the signals are a problem also, wherever the back end of it of control, because you might come up with a very good system, but then you see some of them which are even not working or they are not adequately controlled. For example, how do you determine which side gets a higher flow and the one gets a lower flow and all that? Or again, this is not part of this particular model that you have, or that is another area of science that you don't get into in this model?
Okay, Prof, that is a very good question. Actually, that is what I'm trying to address because what we have there in the CBD at the moment, we have time-based control algorithms. Time-based in the sense that you have the counters. So the red light is given like 60 seconds, especially in the morning, but you find the green time is given 20 seconds, and they don't care of the density of traffic at any particular road. But when you come to this dynamic and learnable model, then through the use of sensors and cameras, we are able to determine or largely estimate the queue length and provide and trigger the green time depending on the length of the queue or on the density of traffic on one particular road. And that way, we are able to address that imbalance, the one you are saying. There might be more vehicles on a particular road, but we allocate the same green time to another road which does not even have vehicles, making the intersection to be even more chaotic. So my model, the deep reinforcement model, is supposed to, it is dynamic, it takes care of the density of traffic and allocate the green time depending on that particular density of traffic on that particular road. If the road does not have very many cars, then there is no need to open it. Or if we open it a short while. But the one with the longer queue length, or the one with the longer, or the one with the more density of traffic, is allocated more green time. And that is where our system, the current existing system, they have not been taking care of the density of traffic.
Thank you. Thank you very much, Omina. I think we can look again, get back to Basil. I know we are almost out of time, but Basil, just check if there is. Yeah, go ahead.
I think one last one in the chat. Karuti Kanyinga says there's need to relate traffic congestion to weak rule of law and culture of impunity. Secondly, there's a class dimension too. In low-income areas, you are likely to see more breaches than elsewhere. Finally, speed bumps are the result of failure to comply with the law. We may want to relate these to dimensions of the model.
Okay, James Omina,
That's it.
What is coming from Professor Kanyinga. Do you have any comment on that? Professor Kanyinga, are you online? Prof. Kanyinga?
Yes, I am online.
Yeah, I would like to hear your voice a bit, because also we didn't have Professor Kamau, and Professor Kanyinga is our outgoing director. It's hardly 2 months when we shifted from one director to another, and it's good to hear his voice and to also appreciate that he's with us. So you can just articulate that your question, Kanyinga. Yeah, go ahead.
Thank you very much, Winnie. I've joined the discussion, even though I joined a little bit late because I was held up in another meeting. But the point I'm making is close to what Ken Ombongi put here. Let me begin by pointing out that what I find in a majority of African countries is traffic is seen to be highly disconnected from the society in many ways, because it's like saying modern technology and traditional technology are working parallel to each other. And therefore, societies with a very strong culture of rule of law are likely to have much more adherence and compliance with traffic regulations, because the law is seen as punishing. But in instances where the law is very weakly enforced, then we are likely to see people are not complying with the traffic regulations, and the law is seen as something foreign and far away. It's a balloon that hangs over the society, and that's why I'm saying, even when you look at low-income areas, you are likely to see breaches, because it's in these areas where, again, modern statutory law is seen as very foreign. It has got a foreign connotation. So that's the point I wanted to bring. And in fact, this relates also to the way I see speed bumps. And if you look across Africa, you've noticed that actually the more the speed bumps on a road, the more those people don't obey the law. Even in Kenya here today, if you are traveling to Meru, you are likely to have more bumps than anywhere else in the country, because the Mira vehicles don't have any idea about the law, and even if the law catches up with them, they will pay and go. And if you go to a place like Kigali, you don't get speed bumps everywhere, because again, the culture of rule of law is very deep. And even Tanzania itself, you find traffic bumps very far apart, again signifying the culture of compliance with the law. I'm just bringing it because what we have not done in development studies, it's actually to relate technology to culture, as Ken Obongia said, but I would even stretch it further and say that, and this is, I'm not joking, I'm not joking, Omina, that technology to Africans is actually the way we saw witchcraft in the old days. No, I'm serious. I have in the old days when I was a child, there was a neighbor who was always saying that his car has been bewitched by a neighbor, and they say, well, when I grew up, I realized that it's actually the battery was that was always down, right? And to blame the neighbor for people to push the car, right? It's when I grew up that I realized that actually it's the battery that was failing, right? So we have not been able really to bring a culture into our standards on technology and see what technology, how the technology commingles with culture in different ways. That's the point I was making, but just wanted to say that this debate was very rich, and I'm very grateful for this. Thank you.
Thank you very much, Professor Kanyinga. Omina, you have any observation about this is still falling under our broad perspective of culture? You have any comment?
Okay,
I want to soon call Tuli. Martin, be on the ready, Tuli, to at least say something. Martin is part of the ULI network. Go ahead.
Okay, Prof, why we normally do modeling in research is because we want to reduce the cost of doing research. If you are to do research on real system, you find the research can be a bit expensive. It can be a bit expensive, a bit dangerous, and so on, and so many other things. So when we model, we just want to prove a certain hypothesis. And when you are modeling, there are certain assumptions that we will make. For example, in my model, we shall make assumption that all the drivers are disciplined. Probably they are not pedestrians crossing the road, because we want to, our model, just to focus on what we want to achieve. And when it comes to these cultural issues, these can be addressed by other forums. For example, in our Kenya Transport Research Network, where we always have all the stakeholders from the ministries, from wherever, from the police, the issue to do with traffic offense in Africa and even in Kenya, we all know what happens with the police. We don't want to go there. So if we can create culture awareness and tell them that, look here, we don't have to dismantle what we have already put in place. I don't know which forum we shall use to escalate such kind of what we want the customer, I mean the citizens to do. But actually, whatever is happening in Africa, it is like the government has not found a mechanism of making the system to be to work. All the systems, not all. You see, when you just focus on one particular system and the other systems are not working, that is where technology now cannot even work. But in a situation where the people who are being served, they know what it takes for technology to be implemented, then the technology can work very well. We have other systems, like in the banks, we have the ATMs, we have others like Safaricom with their M-Pesa. People have been obeying whatever technology is being offered by Safaricom. So when it comes
Thank you very much. I think I'll call upon Martin Tuli. And Tuli, feel free to introduce yourself briefly before you bang on after listening the whole afternoon. Thank you.
Okay, thank you very much. It's been quite an inspiring afternoon. I'm Martin Tuli. I'm Professor of Operations and Project Management at the Loughborough University, Loughborough Business School, Loughborough University in the UK. And prior to this, I was based in Ghana at the Ghana Institute of Management and Public Administration. So my background is in infrastructure and project management. I find today's discussion quite fascinating, and I am really glad to see how James has engaged in this debate. He's been thrown into the lion's den, and I think he's survived.
Thank you, thank you.
And I think this is exactly the vision that we have with the ULI network, that we can engage our PhD students and researchers as they tackle these very complex problems. And as today demonstrates, there are always a lot of elements that we can look at or consider as we look at these problems. And by considering a broad and varied perspectives, it enriches the kinds of research questions or the way we are carrying out the research, and ensure that the eventual output or outcome of our research will have broader application and impact to solve the challenges that we face as a continent. And we can already see that, as Winnie put it, whether, although not intended, we can already see, and James has strongly, addressed the issue of how his work aligns with this idea of symmetry and so on. So I think most of the issues have been debated, and as I was listening as well, part of my thinking was around how this model will address the issues around how perhaps in many cases in Africa, we want the technology to work for us rather than the way it's intended to. And I think part of the questions and discussions I've tried to address this aspect as well. So all I will say is that I'm really glad to have been part of this session today, and it's only giving me a lot of encouragement that we need to continue to engage in these debates, particularly with our researchers, so we can expand their thinking and expand the ways in which their research can be more meaningful. And thanks to James for standing up to the challenges we've thrown at him, and I'm sure this will only enrich his research and that of others. So thank you very much.
Thank you very much, Martin. That's great. I don't know whether we have any other ULI Lose Network member on platform. I can't, maybe I've not looked well. Fred, do we have any other person before we close up who would want to observe? No?
I haven't checked, to be frank.
Yeah,
I haven't, but
difficult
if
to
they
check.
find the person that put up his or her
They
hand,
would have
so
put up their
I
hands,
think
yeah.
that's
So that's so good. I really want to appreciate this forum. For me, this has been a really good engagement. Having worked with Omina from when he was conceptualizing his work to where he is now, and the kind of engagement he has had, because we're really trying to put these things into real life, because it doesn't, technology is good. We do agree technology is good, but technology has to respond to the challenges that we are facing. So if we are having the perfect model of a traffic simulation that will cost so much, but nobody's obeying or respecting it, then that's another issue. So, and that's why we say in our unique context of Africa, we really have to look for what other options do we have. If one option doesn't work, like I know signaling and control is a big issue. We have them posted all over, but they're not working at all. Either they have not been serviced or maintained. So when we hear of new, research coming up, which is going to improve a system that can enable access and mobility in cities, we get very keen to hear what does it have in store? Is this going to sort our usual problem? And of course, if you leave, as Omina has ably illustrated, that there are some parameters that he did not conceptualize the model with, but they can always be thought through on how to accommodate them, all notwithstanding with all these challenges, even of data. So I want to sincerely thank the three, Fred, Omina, and Professor Pio, I really want to sincerely thank you for making our afternoon and IDS seminar a very, very interesting seminar. And for all the participants and contributors, including those who have done through typing and those who had a chance to talk to us, this has been good. And this is what we are for as the Institute for Development Studies. And we'll continue having these similar, platforms, either with ULI or just IDS as it is. We have our regular seminars. I'm sure right now Basil has in store for us. And as we began, Basil began with us, and I'll take it back again to Basil so that she'll be the one to have the last word before we call this a day. Basil? Did we lose Basil?
Thank you so much, Prof. I'm here.
Yeah, good.
So mine is also to add on to your voice, a very big thank you to everyone. And not forgetting, this was also part of the KTRN, our Kenya Researchers Network. I've seen quite a number of members joining, and thanks again. We also look forward to seeing all of us and others in our upcoming seminars, and I'll be sharing the links as usual. Remember to write to us at ids@unbi.ac.k. That's all from me, Prof, and thank you to everyone. Good afternoon.
So now everybody can put their camera on, and Omina, remove your PowerPoint from the scene so that those who want to see each other as people exit can see. Omina, just get off the PowerPoint. All right, so thank you very much, all of you, for those who are able to participate. All the best. We'll see you again.
Thank you.
Thank you. Thank you.
Bye, 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 everybody.
Thank you.
Bye.
Thank you and bye.
Thank you.
Okay, bye, Prof.
Bye, bye, bye.